Hello everyone, welcome back to Machine Learning and AI from Scratch. This is episode 5 and this is the one you have been waiting for. We have built the foundation. You know what machine learning is? The tree types, the full pipeline, and your environment is ready. Today, we put all of that to use. We are building your first real machine learning model from scratch, that is linear regression. This is the algorithm that started the field of modern statistics and still powers more real-world systems than almost any other. By the end of this episode, you will have trained the model, read its output and understood every number it produced. Let's go. This is the agenda. 5 things there. The intuition behind the linear regression, the equation and what each part means, how the model learns, live code, train your first model, and the final is read and interpret the results. Before any math, let's get the picture right. Linear regression does one thing. It finds the best straight line through your data points, then it uses that line to predict values it's never seen before. On the right side, look at the diagram. Each blue dot is a train example, a house we have seen, with its known size and price. The orange line is what the model learns. Is the line that comes closest to all those dots at once, the best fit line. Now the amper dot sitting on that line, that's a prediction. We ask a model, what does a 250 meter square house host? The model doesn't know, but it follows the line to that point and gives us the answer. That's it. That's a linear regression. Find the line, use the line. The only question is how does it find the best line? That's where the math becomes. The equation looks intimidating at first. Let's break it down one symbol at a time. Y head is the prediction. It is what the model outputs the given input. X values are the features. The inputs we provide: size of the house, number of rooms, location, age of the building, whatever you feed the model. W values are the weights. These are the numbers the model learns during training. Each weight tells the model how much that particular feature influences the prediction. A high weight on median income means income is a strong predictor of price. B is the bias, a constant that the model also learns. Think of it as starting point. It shifts the entire line up or down to best fit the data. At the bottom of the side, the simplified version with the one feature YH is equal to WX plus B. You learn this is in school as Y is equal to MX plus B. Same thing. In machine learning, M becomes W and we call B the bias instead of the Y-intercept. The concept is identical. With multiple features, the model finds a hyperline instead of a line, but the method is the same, just extended into a more dimensions. Here's the path that ties all of the ML together. 3 steps, running in loop thousands of times. Step 1, make a prediction. The model starts with random weights. It doesn't know anything yet. It takes its random weights, plugs them into the equation, and produces a prediction for every row in the training set. And the step 2, measure the error. It compares each prediction to the actual known answer. If the real house price is 300k and the model predicted 250, that's the 15k is error. We don't just add up the errors, we square them first to penalize large mistakes for more heavily, and then take the average. This is mean squared error or MSE. The formula is at the bottom of this slide. The smaller the MSE, the better the model fits the data. And third one is adjust the weights. Here's where the magic happens. The model calculates which direction to nudge each weight to make the mean squared error smaller. It takes a small step in that direction. This process is called gradient descent. It's the engine behind the literally all of machine learning. Neural networks, transformer, everything all use some version of gradient descent. Repeat steps 1, 2, and 3 thousands of times. Each time the line shifts slightly closer to the data. Eventually the error stops improving meaningfully and training is done. Now load and explore the data. Open your Jupyter notebook. We are using California housing dataset. It's a build directly into scikit-learn, so there's nothing to download. The first 5 imports bring in everything we need. Fetch California housing, loads the training data, train test split. Let us hold out a test set. Linear regression is the model itself, and the two metrics functions give us mean squared error and R². We then load the data set, split it into X, our feature S data frame, and Y, the target variable. Median house price in hundreds of thousands of dollars. Print x.shape should return 20,640 rows, 8 features per row. If you see that, you are good. Always call X head. Before training anything, look at your data. Know what's in it. The 8 features include median income, house age, average rooms per household, population, and geographic coordinates. Median income turns out to be by far the strongest predictor. We will see that in the weights. Now the model. This is where it all comes together. Train test split with test size equal to 0.2, use 80% of the data for training and holds back 20% for testing. The random state is equal to 42, just makes the split reproducible. You will get the same rows every time you run it. Linear regression creates a blank model object. No learning has happened yet. It's like an empty brain. Model.fit xtrain, ytrain. This is the line where learning actually happened. Scikit-learn runs gradient descent internally, iterating until it converges on the best weights. It looked roughly 1 second. Internally, that was thousands of iterations. Model.predict xstats applies the learned weights to 20% of data of the model has never seen. Then we compute mean squared error and R² and print them. You can see the output MS is equal to 0.56, R² is equal to 0.62. Now reading the results. Two numbers, let's read them properly. Mean squared error of 0.56. Our target variable is in units $100,000. So to convert mean squared error to dollars, we take the square root. 0.56 equal to 0.75, which means an average prediction error of about $75,000. On California house prices that range from 15,000 to 500,000. That's not perfect, but this is a linear model with zero tuning on its first run. R² of 0.62. This is the more interpretable number. R² tell you what fraction of the variation in the target the model explains. 0.62 means 60%. We are in the good range on the scale at the bottom of this slide. The remaining 35% is either noise, nonlinear relationship we can't capture with the straight line, or features we haven't included yet. Now look at the learned weight in the formula bar. Met Inc. has a weight 0.84, the single strongest predictor. Higher median income strongly predicts higher house price. Latitude has a weight of 0.42. House further north in California are generally cheaper. These weights are the model's learned understanding of the data. This interpretability is one of the linear regression's biggest advantage. You can always explain exactly why the model made a prediction. Linear regression is the right tool when you are predicting a continuous number. The linear relationship between your features and the target is roughly linear, and you want an interpretable model that you can explain to a stakeholder. It's also ideal as a baseline. Before building any complex model, always train linear regression first. If your fancy neural network can't beat it, something has gone wrong. Avoid it when your target is a category. That's a job for classification. Avoid it when the relationship is clearly curved or has a sharp threshold. A linear line cannot represent that. And avoid it for images, text, or sequences. Those need deep learning architecture that we will cover in page 3. In episode 6, Understanding Your Data, we'll go deep onto data exploration with pandas and matplotlib. Before modeling anything, you need to see your data, distributions, correlations, outlier. On episode 7, we will have model evaluation, the full story on overfitting, underfitting, every metric worth knowing. In the episode 8, we will see logistic regression, your first classification model predicting categories instead of numbers. So that's all for today. You just trained your first machine learning model, and here's the most important thing to take away from today. Linear regression did not just teach you one algorithm, it taught you the three ideas behind all of machine learning: predict, measure error, adjust. Everything we build from here: neural networks, transformers, reinforcement learning, and agents. All of them do exactly those three things. The implementation gets more complex. The core loop stays the same. Drop your R² score in the comments. Let's see what everyone got. Subscribe for episode 6 and I will see you there. Thank you all.